Okay, great. Thank you. Yeah, I just have a few slides to present on some ongoing work to generate ever denser and higher yields of electron-positron pairs using lasers. And I also want to touch a bit at the end on some of the experimental challenges of doing these kind of measurements and the work that we're doing to try and overcome that. Yeah, so mostly it's a team from LLE, but continuing on from work I was involved in when I was doing my PhD. Yeah, so just briefly, we've seen a lot of this background material before, but experiments that have produced the highest yields of electron-positron pairs at relativistic intensities involve generating electromagnetic cascades triggered in high-Z solid targets. And this is done typically in one of two ways, using hot electrons produced by directly hitting the target with the laser, or by first producing an electron beam that you can drive into the high-Z target. Yeah, and both of these have their advantages. You can produce a larger number of positrons by directly hitting the target, but it's a lot less challenging to produce quasi-neutral pairs if you first produce the electron beam. And then, yes, but in both of these cases, pairs typically have very non-thermal type energy spectra with tails extending into the tens or hundreds of MeV. Yeah, and then looking into the crystal ball of the future, we have the strong field regime where we might be able to study these different processes to produce pairs, but I'm not going to talk about these today. Yeah, so it's kind of a figure of merit. If we're interested in studying collective pair plasma processes with facilities that already exist, is comparing the number of pairs per pair plasma device sphere. And you want this number to be much larger than 1. So if you have this relativistically hot pair distribution, like we typically have, a lot of people sometimes assume a kind of fluid model of the pair population, which assumes that it's like a monoenergetic pair distribution propagating at some gamma factor. But probably more rigorously, what you want to do is assume some kind of isotropic distribution function where you can easily derive a Debye length that has an associated temperature. And it turns out that you can do this in a Lorentz-boosted zero momentum frame and approach at the kind of pair distributions that you can see are produced from Monte Carlo modeling. So you can do this for the distribution of your choice. So if you choose a Maxwellian, like a Judner type distribution, then you get this expression for the Debye length, which is related to the plasma skin depth, the pair plasma skin depth, with a factor that's related to this normalized temperature. And then you can find in the laboratory frame, based on this additional gamma factor, which is parameterizing the zero momentum frame, how many pairs for what temperature and gamma factor you need in order to approach this collective pair plasma regime. And yes, Gianluca already showed this kind of plot. This is the kind of the landscape of where things sit at the moment. There's a recent experiment from Dean Rusby and Hui Chen where they produced slightly more pairs from this direct laser scheme. But yeah, this is where we're sat at the moment. So I've been investigating the possibility of producing quasi-neutral pair plasmas and what we can do using existing laser facilities. And kind of the brute force way to do it is to just produce as many relativistic electrons as possible and then slam them into the high-Z converter. So this is kind of what we're doing here, where we use a mega EP and produce very large number of electrons, nearly 10 to the 13. It's called we have a microcoulombs of charge, so I'm going to just call this microcoulomb class electron beam. And then we have a high Z converter, and then we have some diagnostic. This is the electron-positron proton spectrometer, which is commonly used on these large laser facilities, but it's just a magnet stack with some shielding on the front and image plates inside. Yeah, so if you look at this amount of charge for the energy distribution of these kind of beams, it indicates that we may be able to produce something like 10 to the 11 pairs where we're approaching quasi-neutral kind of regime. So the other advantage is that these beams are produced in a very small volume. We have a millimeter cube size volume, so we can get densities around 10 to the 14. And then if we assume some reasonable gamma factors for the temperature and the mean gamma factor, we get some number which is getting right on the cusp of being able to do these kind of experiments. So maybe some clever little boosts, or we get lucky and we get some very high charge beams. We may be able to start doing these kind of experiments in the near future before these facilities that are coming up, the 10 petawatt class facilities, are coming online. And the other advantage is that we can use these kind of experiments to learn how to diagnose these kind of pairs. So yeah, they're definitely very useful. Yeah, I'd like to have a few more minutes. Okay, so one of the main challenges of measuring these kind of pair beams is that with some configurations, it can be very difficult to measure the positrons with signal-to-noise ratio larger than 1. So this is from some experiments which were a similar configuration to the last slide. And you can see there was a thinner converter used than needed to get a quasi-neutral beam, but you can see in this case the electrons on the image plate, but you can't see anything. This is all just background on the positron plate. And so when we did some Fluker simulations modeling how these pairs hit the front of the spectrometer, we find that there's a tremendous amount of background which is produced, and in this case it's most likely masking the true signal that we want to measure. And so in this case we have a very small opening. This is a millimeter size aperture for the spectrometer, which is necessary to ensure you have energy resolution, because you need, in order to distinguish what is actually the energy on the image plate, you need a small source size. Yeah, so ideally you have a spectrometer which has a shielding that's carefully designed so that the signal-to-noise ratio is much larger than 1 in this highly noisy environment where you're producing secondary cascades wherever you have shielding. And also you really want to collect as large a solid angle as possible. So pairs in these experiments may have divergences tens of milliradians. They've also got variable pointing. This is also a characteristic that there will be in these future strong field QED experiments where pairs are going to be emitted into very large angles and also in relatively small numbers. So yeah, efforts are underway to develop a high flux version of the electron-positron spectrometer at the LLE based on a sector magnet design. So this is the idea for a spectrometer where if you carefully design the shape of the magnet and the shape of the image plate, then you can get the system to kind of work a bit like an achromatic lens, where you have a diverging source that images at different positions, except with charged particle beams instead of light. And so this is showing, we're modeling, including fringe fields in this case. You can see the focused energies. You can basically design this for any range of energies that you like, depending on the size of the magnet and such that you want to choose. So yeah, this is now getting into the more advanced stage of the development. This is how the whole thing is looking. And you can see what's very different about this kind of spectrometer which has got this massive aperture on the front for collecting particles, which means that we should be able to collect something like 400 times larger solid angle than the current EPPS. Yeah, and we've just been doing preliminary modeling of this with the hopes of getting it through design and engineering for experiments in the coming year. But we're using some very state-of-the-art particle tracing of these kind of beams. You can see here we can get energy resolution of 2%, extending into hundreds of MeV. And then we also have additional Fluker modeling where we're studying the kind of precise background that we should get in these kind of experiments and comparing the true signal that we measure to these to make sure that the thing's going to work. And yeah, like I said, we're currently optimizing the design for this 5 to 300 MeV range, which is where we expect to produce most number of pairs from these electron sources that we have. But yeah, you could feasibly conceive that it could be optimized for many hundreds of. Oh, sorry. Yeah. Just to summarize. Yeah, we're investigating how we can use existing platforms to develop high-yield, high-density, quasi-neutral sources for pair plasma and lab astro, and yeah, robust diagnostics such as these are essential for these and future experiments. And yeah, I just wanted to advertise the spectrometer that we're developing. Thank you.
All right. Thank you very much. Have we got any questions? Yeah.
Thank you. So this is a naive theoretician question, but in this magnet, you show it's like discrete. It looks like you have discrete division of energies. It's just your input parameters,
yeah.
or
yeah.
So in reality, your beam will be all over the place, right?
Yes.
Yeah. Okay.
It's just to show there's just a number of discrete energies modeled.
And how complicated would it be to have this extended to 1 GeV or more? Because in some cases for the experiments at Rochester, you could expect positrons, well, 1 GeV, 2 GeV, maybe in this range.
Yeah, well, so that kind of then depends on your other constraints. So we're designing this to be small enough to fit inside the 10-inch manipulators to do the experiments on the Mega EP, so that limits how far we can put away our image plates and how much we can deflect them. You can also make other design choices, like make the magnets really close. So we have like we probably have like a 0.6 Tesla strength, but if you had more like Tesla scale, but there's also trade-offs, but then you're accepting less collection solid angle. But I think it's very possible that you could build something like this for GeV scale if you were willing to build a scary enough magnet.
Okay, we've got a couple more questions. Maxim, do you want to look at? I think that should work.
Okay, yeah. I really like that magnet block, and I'd like to make a comment following. We had several talks that were aimed to achieve quantum effects in the laboratory in laser experiments. And there is one step that I think hasn't been explored properly, and probably that step won't work in the laboratory, but it is interesting for astrophysical applications. And that's the effects of a guide field. And the trick is that if you have a guide field and circularly polarized nonlinear wave, then the particle, the resonantly rotating particle, may get much larger transverse momentum than just A naught. If you have a guide field larger than the driver field. And large transverse momentum, that's kind of good, that pushes us more towards this fully quantum, towards the quantum effects. And this regime might be very important in astrophysics. And as I say, maybe if not in the laboratory, then in peaks this could be achieved.
I don't think that's, yeah. I don't know if that answered that.
I think 50 Tesla is about state of the art for the pulsed magnetic fields you can achieve in the lab.
Hi, Charlie. Very, very good talk. Maybe it's kind of a technical question, but I'm kind of adverse to image plates. Have you thought of a different design which doesn't use image plates? For example, scintillators or time peaks?
Yeah, I have been looking at this as well. There are a few problems with this. Ideally, yeah, it would be great to have also live data. But one of the main problems is, yeah, I don't know how tested some of these things are for EMP, which we'll almost certainly have problems with. I have been looking at the possibility of having some kind of scintillating fiber array, but it seems that there is not too much of an appetite for this, so that's probably going to be an extended version of this spectrometer at some point. But yeah, that's almost certainly going to be necessary when you go to like 5-minute repetition rates. Yeah.
Any other questions for Charlie? All right. Well, if not, I think this is a great place to close the pair plasma session. Thank you to all the speakers.